Hello, friends. Welcome to the Georgia Tech AI podcast. My guest today is Harish Ravichandar, an assistant professor and core faculty member of the Institute for Robotics and Intelligent Machines. He directs the STAR Lab, Structured Techniques for Algorithmic Robotics, that's focused on developing learning frameworks that enable robots to be reliable, efficient, and adaptable to this dynamic, messy, unpredictable world that we live in. He's also focused on making robotics accessible, ensuring that this technology can one day be used by just about everyone. He also believes that scaling isn't the only path to developing intelligent machines. The one thing that strikes me about Harish is his relentless curiosity and humility. He's a skeptic at heart, always questioning ideas, trying to get to the bottom of things, but he's also willing to try new stuff. And he doesn't mind struggling with things in the beginning. So, speaking with him almost felt like talking to a friend who's just as curious and who's just as passionate as you are. And now, dear friends, please welcome Harish Ravichandar. So, your lab's focus is on building reliable robots to operate in dynamic, unstructured human contexts. So, could you start off by painting a picture for what success to you looks like? What is the kind of future that you'd like to unlock?
Yeah. So that is a very good question. So if I try to imagine a hypothetical future um, that I would like in terms of what robots would be capable of, it very much looks like a robot that has intelligence that mirrors that of humans. Because in many of my uh, research projects and many of the research projects in the lab, we try to focus on how do we really get robots to be able to acquire skills, adapt their skills, and respond in adaptive environments and humans, things like that, very much in a very fluent way. So the goal of doing this is the end of the day, the world is built by humans and for humans, right? At least that's how it's been so far. And in my opinion, the seamless way to integrate robots into our lives in whatever shape or form looks very much like something that we wouldn't have a hard time accepting, and something that would be useful, and something that would also make our lives better in some way, shape, or form. Typically, these things tend to be correlated in the sense that it's very difficult to have a technology deeply impact our lives if you are not going to accept it. And to some extent, I'm not sure who's attributed to this quote, the quote of any sufficiently advanced technology should look like magic. That's kind of what I'm really trying to achieve, in the sense that the robot should be able to seamlessly generalize, should be able to seamlessly adapt to situations like humans do. When humans do it, we don't even think about it, right? It has to be another way to think about that quote is sufficiently advanced technology should be invisible, in the sense that you should not even realize that you are pretty much interacting with a robot. It should feel like you're just interacting with another intelligent agent. And in a way, if you think about the chatbots and why they have been very successful, that's kind of why. If you think about essentially the Turing test, these chatbots would be able to pass them because people can't quite tell. You can't quite tell if this is just a person with a particular quirky personality. Of course, there are lots of like signs that you could use to decipher, but this is not something common person who doesn't have insider info will be able to do, right? For example, they kind of tend to be sycophants. They don't quite push back as humans would do, things like that. But at the same time, in a relatively short amount of interaction, you can't quite tell because you might just think that's just a very polite person and a very agreeable person, right? Similarly, how do we make this happen for robots, right? So because now the challenge is it's not enough to just be able to hold dialogue and have a semantically meaningful conversation. You have to intelligently interact with the real world. So that is, I would say, is just a very general, relatively vague, long term dream or desire. And of course, I'm not even remotely alone in this dream. Almost all roboticists kind of have a version of this dream, right? In one way, shape, or form. I guess where we differ in this is the way in which we want to achieve this, right? So the way in which we want to achieve this, from that perspective, we are particularly interested in techniques that would help us be able to do this efficiently. So in fact, we think about multiple dimensions of what our technology should really look like, or what kinds of intelligence should look like for robots. One of the first things we focus on is efficiency. And efficiency is both from a data perspective as well as compute perspective. So this is once again, the motivation is going back to if humans are able to be very efficient, sample efficient, especially when they're generalizing. Of course, you could have arguments about how sample efficient humans really are, given how long our childhood is and how long it takes to perfect motor skills. But regardless, once a skill is acquired, generalizing that skill to completely unseen situations, objects, scenarios, whatever it is, seems to be very straightforward for us. So even if it's so bizarre, it might just take maybe one or two shots of looking at what the situation is and be able to quickly adapt to that. So how exactly do we develop algorithms that mimic this kind of capability is one question. And similarly, we also have relatively limited compute. We have what's called bounded rationality. We cannot think beyond a certain level in terms of just numerics. We can't just solve complex optimization problems in our heads. But nevertheless, we are able to effectively operate in this world very robustly and in a very resilient manner. So one core dimension of our thinking or philosophy is how do you really get robots to be able to do something like this? And another dimension is not relying as much as possible on experts. So when I say this, there are a couple of different ways to look at this. One way to look at this is the robot does not rely on any experts when it's being used, in the sense that once you deploy the robot, you don't really want the robot to rely on experts. You can also think of this as the robot never relies on an expert, almost as if like it's able to completely in a self-supervised fashion acquire a lot of skills. So while the second sort of self-reliance is interesting, I'm a lot more interested in the former. Why I say this is, in my mind, I don't really care if it takes my lab a whole year to think through, carefully design, and craft a particular algorithm for a robot. But for me, what really matters is once we are done and we deploy this, can this robot now effectively operate and generalize across a wide range of circumstances without requiring me again? So this would look like, from a technical perspective, you want to design algorithms and frameworks and models that can adapt to new situations, learn new tasks without having an engineer design a new reward function every time something changes. Or this could look like, oh, you really want now a new architecture for your neural network because this task. The goal really is how can the robot either with the architecture, the reward design, whatever sort of design goes into these algorithms, how can the robot just use the same design and apply to across all these situations? Or even if new designs are required, could the robot figure this out itself? So that's that's intuitive way to think about this is I'm very interested in learning like humans as opposed to just learning from humans. So the idea is to see how we can develop robots that can learn like us, in the sense that we routinely encounter situations we can't quite handle. And we just are very good at robustly picking up the skill in an efficient manner and robustly executing it. How can robots do this is one fundamental question. So that's where the reliance on expertise comes in. I don't care about the offline reliance on expertise as much. I'm fine studying an arcane mathematical topic for a whole year just to figure out like, how do I design this particular policy architecture or this objective function or learning algorithm, whatever it may be, as far as it would then, when deployed, generalize for me. And on the other hand, we have talked about this efficiency dimension. We have talked about this sort of the dimension of self-reliance or not requiring as much expertise, at least during operation. There's one more dimension that we care about, which is what I've been starting to call translucency. So the reason why I call it translucency is full transparency is quite difficult in the sense that ultimately, whatever you do, it's going to be very difficult for you to fully explain what the robot is doing and why it's doing it. This is because inevitably you're going to have modules, you're going to have at least small parts of your robot's overall approach and framework that is just learned from data that you can't quite explain. In fact, if you could very well explain, you might have as well just manually encode that. right? Sometimes you can't, you don't quite know. And the way in which I usually defend this is we should not pretend like humans are transparent. We are not transparent as humans. Many times we don't know why we are doing what we're doing. And there's quite a bit of almost humorous studies in psychology that show how we do what's called post hoc rationalization, where we make stuff up when we are asked, why did we do something? So that tells me that we, even to ourselves, forget, let alone communicating this to another person, are not very good at understanding why we do what we do. But at the same time, we are also not completely clueless. We have a relatively decent guess. And more importantly to me, what I care about this translucency is predictability. So this is something we have been thinking about lately. This is a relatively new space for us for the lab. It's just that sometimes we get this as a natural consequence of how we design our algorithms, but this is not something we have particularly focused on until recently. So this is the challenge of how do you think about the problem of explainable AI in robotics? And one way to think about it is maybe what you care about is not explainability, but predictability. Because essentially what we really want is the ability to foresee what this other agent in our environment is going to do. As humans, we are really just interested in seeing how predictable are the people around me, right? It could be other humans as well, right? That's what we are really looking for. You're driving a car, what you expect is predictability. You don't care why a person changed the lane. It doesn't really matter to you as far as you're able to anticipate that they change the lane. So in a way, the way to think about this is you really want to make it easy for humans to do anticipatory planning, which is what we do routinely. And the way to do that is to somehow make it such that it's easy for the humans to model your robot, which will require the robot to be consistent. It would require the robot to be reliable. It would require the robot to have some notion of robustness across variations. So essentially, there are lots of these potentially uninformative and not relevant signals that the robot should not react to. So it should be insensitive to those and only sensitive to things that actually matter for the task or the behavior. This would increase essentially the predictability of the robot. So how do we really think about this? And one of the ways in which we have implicitly gotten at this problem is develop approaches that come with some form of theoretical guarantees. So when you have theoretical guarantees, it's almost an extreme version of this, but you're saying no matter the circumstances within which the robot is going to operate, within those circumstances, the robot is always guaranteed to do something. One of the very straightforward guarantees to think about and implement is having stability for your robots. So stability is from a very dynamical systems perspective here. But ultimately what that translates to is this could be a learned policy, but I can always guarantee that it's never going to do anything very dangerous or swing its arms and throw stuff around, right? But of course, the real challenge that we have not even scratched the surface of it is what exactly functional safety looks like. This is something that many of my colleagues are interested in. I'm very interested in learning from them and incorporating some of these ideas in our own work. I myself am not an expert in safety, but I do find the notion fascinating. So how do you have these translucent models that you can kind of guess what they're going to do, what this robot is about to do, and have the predictability built in? So I would say these are the kind of motivating dimensions for how we get to the vague dream that I described at the outset. If an alternative dream could be, I just want to build a very scalable pipeline for robot learning. I just have lots. I'm going to enable the collection of large amounts of data. I'm going to enable the training and inference of large models, right? That's a completely parallel perspective to this problem. I am personally more fascinated with what I laid out as sort of the three guiding dimensions or principles that we use in almost all the projects that we do.
Absolutely. Let's talk about the parallel routes that people are taking to this goal. So one of your talks, it was very well crafted. You called it "New Wine in an Old Bottle."
Yeah. Yeah.
So what is the old bottle that
Yeah.
you're
Yeah.
trying to actualize?
So that is just, obviously that's the play on the famous phrase or an idiom. The reason why I used that phrase was the way I think about this is I really want to, from a technical perspective, I really want classical approaches to all serve as scaffolding. So when I say scaffolding, what that means is there are things that we have figured out about the physical world over the last several centuries, starting from almost Aristotle. People have been trying to do this, right, for a long time, trying to figure out different things about the physical world. And robotics, of course, is very much about the physical world because it's a physical entity in the physical world. And of course, in the last century, even within robotics, they've had lots of discoveries and inventions and novel ideas and ways of thinking about stuff. My intention is just to be cognizant of these things and be able to leverage them whenever I can. So what that looks like is I want to use them as scaffolding. Why not just use them directly? Is because the way I think about this is these approaches have been traditionally designed for a very narrow design space. So they usually take a very particular problem, and within that realm, there is a very particular method. But within that realm, that method, the analytically designed or hand designed method, will perform exceptionally well. Almost to the point that you just can't do any better because people would literally come up with optimality guarantees for these methods. So, but of course, what I'm ultimately interested in is in robots that can essentially work in environments that you don't quite know ahead of time very well. So these are the dynamic and unstructured environments, right? So if you want a robot to operate in these kinds of environments, these methods typically will quickly become brittle because you're operating them outside their design spec. In fact, they come with these design specs. You know what those design specs are because they will lay out the exact assumptions. But every time you violate the assumption, you're just basically flipping a coin. It might work, it might not work. There are lots of nuances. So you can't directly use them. But at the same time, I also don't want to go to the other extreme and say, I'm going to just throw them out because they are limited in their spec and completely come up with a new approach. I'm trying to see what I can leverage still, what I can salvage from these approaches. So in my mind, different projects will call for different things that you can steal from these methods. And oftentimes they look like scaffolding because you are getting at the core intuitions from those methods. You are trying to borrow core design choices from those methods, but you are not going to incorporate any design choices from those frameworks that are particular to the design spec. So part of the challenge is, given a problem space, kind of trying to get a sense of like what kind of tools are relevant, classical tools are relevant here, and then going through the different aspects of those tools to identify which aspects of this design were made specifically to fit this particular problem and is actually resulting in this bottleneck. And only get rid of those, but keep the rest that are relatively general, right? So I'll give you an example. So if you think of properties like, I know that energy has to be conserved in a system. I know that at the end of the day, the robot needs to be able to perform a task in a way that's relatively safe and stable, right? So these are very general ideas. They are not particular to a domain or a task. So if these aspects are baked into those frameworks, so you want to just take those ideas. Within those, there would, of course, be other design choices that they would have made to make it work within that design spec. But you don't have to borrow those. That's where you could supplement the framework with learning. So this is why I see them as scaffolding as opposed to just modules you could just throw into your framework. So what kind of scaffolding you could take is the first question. And then the second question is, now how can you combine learning with this? So this would sometimes look like there are elements of this larger skeleton framework where you are replacing modules with learned networks of some sort. That's the most straightforward, relatively simple way to do it. But another way to do it is look at how you would design a learning-based solution and kind of change the way in which you are designing or the robot is learning inspired by these ideas. So sometimes this would look like, I want to use a neural network for this, but I want a certain property out of this. So I need to be able to either regularize or constrain the parameters of my network. Sometimes it looks like, oh, I have this, people have come up with this insight like 100 years ago. It's very relevant here. How can we use it? Sometimes it looks like here's an objective function that's largely almost exactly the same as the objective functions before. But then I'm going to parameterize this objective function because I don't know the exact design spec where I would be deploying these robots. So I'm going to parameterize this and learn this. So why you would do this is essentially you are making the learning problem as easier as possible for you. And this is why I said it's fine to spend a bunch of time in the lab trying to figure out what are these structures and which ones are generalizable, which ones are limiting, because not all structure is useful. And in fact, not all structures are useful everywhere. you kind of have to find out the confines of this. And part of our research is exactly that, right? So we call them, the overall field is, think of it as like structured robot learning, where you're identifying what structures are useful, what structures are not useful. When do they harm the learning process? When do they benefit the learning process? What are the circumstances? What are the boundaries? So in a way, the motivation is to try to come up with the science of structured robot learning, right? So which is something we don't quite have now. So even including work in our own lab, we usually study structures in isolation for certain contexts, and we make them as broad as possible, but still they're relatively limited to some design spec, right? I'm not going to pretend like analytical methods have a very have a design spec and that limits them, and somehow these approaches magically don't have one. It's just that they're broader, right? The goal is to make them as broad as possible, but I'm sure there will be limits to each structure that we use. Some structures are more generalizable than others. So then this becomes a problem of, what do you really want from your robot? You want your robot to have like somehow one model that's just a generalist model that can do everything, versus what you find with having robots essentially almost a bag of tricks of different ways of doing things, and then maybe some other mechanism that helps you choose which tricks to employ at what point. How do you mix the tricks together, right? They're just philosophically different ways of approaching the same challenge. I don't think anybody would refute that ultimately you want the robot to be able to do a lot of different things, but the question is, how do you want to encode that knowledge? We don't quite know which is the right strategy to do this, but my bet is currently on being able to have broad skills as much as you can, but in general, accept the fact that you're going to have modularized set of skills or a library of skills, almost have a planning framework on top of that that is going to help you decide which ones are the most important ones to actually deploy right now. Or if you encounter a new situation, thinking about like, which of my skills from the past are most relevant here. And so that's thinking about the transfer learning problem and figuring out like, how do I fuse the skills that I have? Do I need to learn something new? What do I need to do to learn the new skill? Things like that. So you get to questions like that.
Yeah. Fundamentally, every robotics researcher wants to achieve the same goals. We want more efficient robots. We want more predictable robots. Reliability is paramount. We want transparency, but we have different ways of getting there. And there's been a massive push in this past decade in terms of foundation models in robotics, computer vision, and a lot of good has come out of it. We've seen some really impressive results. Your work doesn't quite align with that mainstream ideology. Oh, and you have a quote that summarizes all of it. Scaling might be sufficient, but it's not necessary. Can you expand on that?
Yeah. So, I mean, it's somewhat incendiary of a claim, I will admit, but nevertheless, I think it's relatively honest in the sense that that's some of my that's my true feeling. But I'm using the word feeling carefully because it is true that it's a feeling, right? Because this is just a hunch. This is not. I don't have evidence to actually back this up. There is no evidence to back up any stance on this debate because it's a very much an unsettled debate at this point. So, but having laid out that caveat, because I wouldn't be a good scientist if I claim and talk as if I have evidence for this. So I want to make it clear that this is just my hypothesis and my personal opinion. So I think of foundation models and research in that space as producing almost magical outcomes. I find them fascinating. I think it would be dishonest if one does not acknowledge the incredible progress that's been made and how nearly magical the performance seems to be, in the sense that I don't think anybody could have anticipated 5 years ago the kinds of capabilities these foundation models are enabling today. I think if you said it, people would probably think you're just delirious, right? It would have seemed so far out, but now these models are definitely enabling that for us. So this is exactly why part of my quote talks about the fact that it might be sufficient, because right now it almost feels like if you just figure out the challenges of how to keep scaling, if you figure out the challenges of how to make the engineering and the systems complexities work, along with the algorithmic challenges of scaling, you really might have something that looks like a generalist robot that can do a variety of things, right? And I have no bone to pick there, right? I'm not even remotely worried about or pushing back against that being a possibility. But my argument is about, I don't know if I'm convinced that that's the only route. So that's why my argument is largely about necessity. So why I'm not convinced is, once again, part of it is essentially looking at how humans and animals learn, right? So I know nothing about biology, but biology does inspire me a lot in the sense that I can't help but think about how we tend to learn, how animals tend to learn in general. And to me, it doesn't look like scaling is how we are doing it. There must be alternate mechanisms to make this happen. And this is from just an intellectual perspective of like curiosity of what are these other techniques that is not just reliant on essentially the scaling. A very intuitive way to think about this is I'm not sure if I really need my robot to be able to quote Seneca if I want my robot to just clean my dishes. That seems unnecessary. But at the same time, I will acknowledge that right now we don't know how to encode common sense into robots in any other way, shape, or form. The only way we know how is let them read the entire internet. Apparently, that's what it takes for them to have common sense, which is interesting in and of itself. I don't know if that's the only way to get at that problem. But for me as a roboticist, what I'm thinking about is what other alternate mechanisms are there? What other kinds of data or amounts of data that you would need in order to be able to get to similar levels of performance? So that's what I'm inspired by, and that's why this is the source for why I make that statement. And the other piece is practical. It's almost an ethical argument in the sense that I'm not sure if I'm convinced that if these models and when these models become truly useful and robust and very effective, I'm not very convinced that these models would actually benefit all of humanity in the sense that there are going to be domains, there are going to be sectors of industry, there are going to be people who simply cannot afford to use these types of models, largely because of the requirements in terms of computation, requirements in terms of data resources that would be necessary. And it's unclear how committed companies would be that are largely leading these efforts in some ways in terms of what the large language models are. Even though the technology might come from academia, many companies are producing these large models, for-profit companies. I'm not sure how long they would be invested in keeping things open source. I'm not sure at what point it would stop making business sense for their bottom line. So these concerns also motivate me to pursue alternate approaches that would be relatively easier for people and industry sectors that can't afford the kinds of resources you need to operate these models. So because it's inevitable that you would have to have the ability to fine tune these models in some way, shape, or form, or at least you need a lot of expertise to even deploy them in a meaningful way. Part of the challenge is this is related to the second dimension I talked about, is also making it easy for people to use the technology in the sense that if I want to make it such that if I put something up on GitHub, and a person with an undergraduate degree should be able to just deploy that technology. You shouldn't need a PhD to make it work. So from that perspective is another angle that I take to this problem of looking for alternative approaches.
See, accessibility is such a huge theme. Even besides your research, I've noticed there was this video that came up, I think it was 2015 from UConn.
God, I don't know what you found. Yeah.
It was 85,000 views. You're teaching electric circuits.
That feels like a different life. Yeah, that is true.
Yeah,
That is true.
wow.
So there was this very nice undergraduate organization called HKN from IEEE, student organization. They wanted to create like essentially lectures that they can freely make available online. And I was very excited that they wanted to do it. So we did a bunch of tutorials and exercises when I was in grad school.
Yeah, you changed a lot.
I'm sure I've gotten much older now. Yes.
I also, when we talk about accessibility, it's also the way that papers come out of your lab. If I really look at the language, it's not too convoluted. It's simple to understand and you get the points across very coherently. I wanted to ask you, what's your process for writing papers that distill complex concepts down so that people can understand it?
First of all, that's very kind of you to say. I'm glad it comes across as that. My process, to be honest with you, is somewhat chaotic. It's not like I have a highly streamlined, disciplined process that I use. So for me, the object of writing is to be able to communicate ideas in a way that make them seem obvious in retrospect. So the goal really is actually selfish in some ways, because whenever we are wrestling with ideas in our lab and we are thinking about different approaches, I usually feel uneasy until I fully grasp that idea. And usually I only fully grasp the idea after I am able to break it down to its principal components and be able to construct it almost from what I already know. For me, everything has to be almost like a graph in my head of connected concepts. It's just the way my brain works. I just can't really understand stuff. I'm very bad at memorization, for example. If I am told facts, I am notorious among my friends for never remembering facts. I just can't do it. I just will forget it immediately. It has to be a concept. It has to be something that I can tie. So everything is like a building block. So if we are coming up with a new idea, I have to have two things. One is I have to have a good intuition. I should be able to explain this to a middle school kid. That's the level of intuition I'm looking for usually. So this usually looks like just sort of like routinely thinking about it, not just actually sitting in front of your computer and writing. Sometimes it looks like that. Sometimes it's just like looking for analogies. Like, what is a good analogy here? Of course, it's going to be somewhat inaccurate, but that's fine. That's the part of the process. It's almost like the famous idiom of all models are wrong, some are useful, to try to find that very useful model for the purpose of communication and not for the purpose of accuracy. So that's from an intuition perspective. So I really look for this, and me and my students look for this. And then when we find it, we really get excited. And that's what we usually highlight in the paper. And the other track is even from a technical perspective, if you want to be mathematically rigorous, want the ideas that we present to be, you should be able to trace it back to ideas you know, almost to the point that you should be able to trace it back to ideas you learn in your undergraduate courses. Right? It has to build up. That requires essentially this understanding of where does this inspiration come from? How can you use basic tools and progressively build to this level? So doing both of this as a part of the writing process is essentially the overall process for me. So, and the way in which mechanistically this happens is I typically write a relatively bad draft, and I tend to be very forgiving with myself. I don't really care what that looks like. I just put stuff down on paper and I just randomly revise it, right? So sometimes I would think of like, oh, that seems like a nice route to get to this idea. And then I'll just try to work it out. And the way I work it out is I write it down. Or I'm also a very visual thinker, so I will draw it out. As I'm doing it, sometimes I would realize, oh, this was a very dumb idea. That's not how this works. Either because like it is missing crucial steps, the analogy breaks down, or the analogy kind of gets it, but it highlights the wrong parts of what I want to highlight. Like it's not highlighting the novelty, it's highlighting like some existing idea. So kind of just being almost very open to coming up with bad ideas is how you just progressively sift through these. And at the end, you're pretty much just like, we are just letting go of the paper, right? You never finish writing, you just let go. So basically at the point of the deadline or whatever it is, of exhaustion, whatever it is, you're like, okay, fine. This is the best I can do right now. So I'll just ship it with what I have. So is how it happens. I almost always look back at whenever I look back at my older papers for whatever reason, I always think like, could have said that better. So I continue to feel that way all the time.
That's a good sign. That means you're growing, right?
Apparently so. So I'll take it. I'll take it. Yeah.
There's this really interesting story I wanted to ask you about. It's related to one of the key breakthroughs in your lab with Koopman operators. I'll let you explain it later, but I wanted to paint this picture for you. So one of your PhD students, Yunhai Han, he walks into your lab and says, this second order lifting worked really well, and I think we have a result on our hands. And you were extremely skeptical.
Yeah.
So could you talk me through the background that went into this interaction, and also why were you so skeptical?
Sure. I think it would help to kind of provide a basic intuition for what Koopman operators are, and then go from there. This line of work is essentially trying to take a look at an idea that's nearly a century old. I think the first paper, Koopman, was a scientist who came up with this particular idea, I think in 1930. So the core idea is about dynamical systems. So the primary argument is if you have a nonlinear dynamical system, typically what you can do is you can either use nonlinear tools to analyze that system or control that system, whatever you want to do with that dynamical system. Or if you want to leverage linear techniques, what people would do is people would just linearize. So when you're linearizing, of course, what you almost always do is you will do local linearization. So this is like, imagine you're taking a tangent on a curve. So that's just the same thing here, except you're just linearizing a system instead of just some arbitrary function. Linearizing a dynamical system as opposed to an arbitrary function. So But Koopman's core idea was that actually there is a way to think about nonlinear dynamical systems that would help us use linear systems theory without approximating the nonlinear system, which means you are almost exactly representing the nonlinear system in a linear space. So this sounds insane, right? At the outset, like how the hell is this even possible? So Koopman's core idea was we should not be tracking what happens to the states of a dynamical system over time. That's what's governed by this nonlinear dynamical system. Instead, we should think of how do functions of that state evolve over time. So here is the core trick. The trick is the functions of states can absorb the nonlinearity for you such that it can produce a latent space where your evolution is completely linear. So this is the core idea. So he went on to prove that you can take any arbitrary nonlinear system and represent it like this in a linear way. This kind of makes sense, but still sounds too good to be true. That's because it is too good to be true in the sense that his proof is very much like the universal approximation theorem. You need infinite dimensions in that latent space for you to guarantee that it will evolve linearly. So this idea was super interesting, but I don't think it really gained a lot of traction and popularity for several decades until and data-driven techniques started working. People who work on those kinds of techniques started picking this idea up, like, I don't know, 1970s, 80s. There are lots of people who have done phenomenal work in this space, foundational theoretical work in this space. So then it became clear that you can actually kind of get away with finite dimensions and just be fine. Almost once again, analogous to, even though universal approximation theorem exists only for infinite dimensional hidden layers, you still get really good performance with finite dimensional neural networks to this day. However large they are, foundation models are still finite, right? And they're able to approximate ridiculously complex functions, right? So the same idea kind of applies here, just that it's from a dynamical systems perspective. So this motivated us to think about, we typically think of robot skills from a dynamical systems perspective. So how I think about it is, we want the robot to be able to guess if this is where you are in your state space of your task or your general problem setting. How do you effectively now decide what should be the next set of steps? And then the controller kind of figures out how to make that happen, right? So that's how we model these skills. So this naturally made it seem like, okay, so far we have been developing algorithms that are stealing ideas from nonlinear dynamical systems theory, which is what we were doing before. It had its benefits. We were able to make a lot of progress, but nevertheless, they were still nonlinear dynamical systems and the tools were relatively difficult to work with. So what can we do with this Koopman operator theory seems very relevant, right? At that point, we didn't know much about Koopman operators. That was just I think I serendipitously discovered it by watching some talk or some seminar where this came up. I was like, okay, sounds amazing. So we'll try to work on this. So Yunhai and I started talking because this was when Yunhai was starting his PhD. And we were chatting and we were saying, like, let's try to incorporate this idea and try to see what happens. And of course, one of the challenges in Koopman-based methods is learning or figuring out what is the function of the state. What is that latent space? You don't quite know. You can manually design it. You can learn it. You can do lots of different options. So we were like, let's try to just do like a very simple baseline experiment. So we wanted to learn dexterous manipulation skills, partly because it's already high dimensional. There are lots of nonlinear dynamics of making and breaking contact, and you want to be able to learn the skill. So we know there are baselines out there that we're using data-driven techniques to do it with neural networks. So we could just at least compare against, like, how does this fare? So just to get the ball rolling, we had initially decided that let's try something extremely simple. We will manually decide what that lifting function is or what that mapping function is to the latent space. And we decided, let's do polynomials, right? Because polynomials are just one of the most basic things you can think of, almost like sinusoidal curves. We didn't do sinusoids because we didn't expect anything to be periodic. So we were like, let's do polynomials, right? It's a very smooth basis function. We'll go from there. So you know how I decided, okay, I'll do a second order polynomial. So now what happens is if you use something like that, you're mapping your state with this polynomial, and all the coefficients are essentially what you don't quite know what those coefficients are. And the coefficients are literally the linear system, in the sense that there is almost like a nonlinear basis function based on your polynomials. And then there is a linear matrix that gets multiplied to it, which is literally the coefficients of that polynomial, so that you can predict what's going to happen next, right? It's a dynamical system. It's autoregressive. So he tried it with the second order polynomial system. And if you now think about the challenge, you've already decided that it's polynomials for your lifting. You just need to learn the coefficients. And learning the coefficients part is actually a linear problem in this. So now the entire learning process doesn't even need gradient descent. You could do least squares, literally just least squares from high school. You could just do least squares and fit a matrix to this data. So obviously, this doesn't take much time to implement. This is extremely easy, like just a few lines of code, and you could try it. So he came back the next day, and I wasn't expecting him to come back the next day. He just came back the next day, and he was like, "Yeah, it just works." So I was naturally very, very surprised because I didn't expect the dynamics to be simple enough for a second order polynomial basis function to capture and be able to learn just with least squares. Because essentially what that means is you just need a couple of seconds to learn manipulation skills with multi-fingered hands, which sounds insane. So I was very skeptical for a couple of weeks, actually. We kept going back, and so he kept going back. Yunhai kept going back and checking his code to make sure like there was not a bug when we are trying to compare methods, and somehow we just replaced the ultimate policy with like an already trained expert policy or something like that. And then after a while, we were like, okay, maybe this actually is working. So that's what led to our first paper in this space of how do you basically now use this very simple structure. Once again, this is like the scaffolding, because that idea very much just provides the scaffolding for how you model these things. Everything else, it was just designed around it to be as flexible as possible. And we saw that, oh, now the same thing works across different tasks. So in fact, we didn't even have to change the basis functions across the tasks we tried, which was very surprising. Of course, there is a limit to it. I'm sure, like, for example, I think we also tried later for like something like locomotion, and I don't think the second order polynomials worked very well. We had to learn something or introduce sinusoidal terms and things like that. And since we have, of course, moved on to challenges where like you generally might not know what this is, or you might have to learn, but the first result really gave us the kind of confidence and the excitement more than anything else that this ridiculously simple technique ends up working so reliably well. So you ended up needing less data. Your estimates are optimal with respect to this policy architecture now, because you're just solving least squares problems. It's computationally extremely efficient. And so this is what resulted in the Coral paper a couple of years back that you and I wrote. So that was kind of the initial story for how this panned out.
Yeah, this is just a general observation, but it's kind of insane how random the research process is. You come across Koopman operators and you decide, oh, what if we incorporated? And then you find a PhD student who's just trying stuff, you're discussing things and you're just trying stuff and something works.
Yeah. I mean, this is pretty much, I don't want to speak for all scientists, but many scientists I know, including myself, this is pretty much exactly what we do. Right? We just are curious about stuff and we just try stuff. What people don't see typically behind the scenes is we try a lot of things, and most things are very dumb. It's because it's just a dumb idea. You just didn't think it through, and you will realize it. And of course, the goal is to realize it as quickly as possible so that you're not wasting your time on stupid ideas. But it's impossible to generate only good ideas. So you try a lot of things, right? So we are talking about this because this turned out to be a good structure. This turned out to be a very productive line of research for us. But obviously, we have also tried a whole bunch of other things that never saw the day of light. That's because we initially maybe thought we were excited about it. We were curious about something. We would try it, and then it might not pan out. So essentially, almost all projects, this is how they happen. You just try different things. You just start making informed guesses. And progressively, what you get better at is you get better at guessing what is likely to work and what's unlikely to work, so that you can be more sort of prudent in how you are allocating your resources. That's pretty much it, right? Otherwise, yeah, you're just trying stuff out. It's almost impossible to predict at the outset how well something will work. But you almost also need this irrational faith in what you're trying to do. So it's very interesting dichotomy of being very irrational in your faith and passion, but following the scientific method in trying to actually produce knowledge and make arguments for your work. There's this book that I really like called The Knowledge Machine, which talks about, it's a philosophy of science book that talks about this tension between how scientists, like in their private moments, have these irrational beliefs that they really want to just make work, but they're not allowed to use that to make an argument. They can only use data to make an argument. So how do you reconcile these things? Because I don't think without that kind of irrational faith and excitement, it will be possible for you to just work very hard, right? You just give up very easily if you don't have an attachment to it. But at the same time, you don't want to attach your entire ego to an idea to the point that if it doesn't work, all of a sudden you feel like you have failed, as opposed to, oh, this idea didn't pan out, I'm just going to try a new one.
Right, right. Wow, there's so much to unpack there. And one observation I see is you're quite the skeptic. You're very suspicious of things. And
I am.
good, I was right.
So I think this is interesting because I think I'm almost too trusting interpersonally with people, but with ideas, I'm very, very skeptical. With arguments, I'm very, very skeptical. It's easy for me to maybe trust a person very quickly, but if they are making a claim, all the devil's advocate arguments are immediately brewing in my head, to the point that I have to be quite careful when I have conversations with my partner.
Yeah. And I also wanted to talk about another work that came out of your lab, CIMER. CIMER argues that imitation without emulation is insufficient. And I would love for you to explain this through the example that you gave about, Cristiano Ronaldo scoring goals. Yeah, could you explain the concepts of imitation and emulation through that?
So the Cristiano Ronaldo, particularly the Cristiano Ronaldo example, came from Yunhai. So generally, the intuition is like this, right? So imagine you are sitting on your couch and watching Cristiano Ronaldo take penalty kicks, and your job is to try to kick like Cristiano Ronaldo, right? So you're sitting on the couch and watching. Some amount of learning is happening already on the couch. You're not even moving, right? But learning is happening. What kind of learning is happening? Things like pattern extractions, things like state estimation of some sort, where you're figuring out like, what is Ronaldo doing? What is happening to the ball? Things like that, right? So you're learning all of this. Typically, imitation learning takes this perspective of the very standard version of, like, for example, if you think of behavioral cloning, you're just trying to essentially do the same things as the expert at any given situation. Now, if you take this particular problem of watching Cristiano Ronaldo and mimicking it, the problem is you don't look exactly like Cristiano Ronaldo. Almost nobody does. Like, our morphologies, even though we're all human, is slightly different. And of course, techniques, number of other things are also different. So you're watching this, you get a basic sense. Nobody sitting on that couch watching Cristiano Ronaldo is going to now conclude, can now kick like Cristiano Ronaldo. Nobody in their right mind will make that claim. Why? Because they know they have never practiced this. So now the second phase is the practice phase, right? So our argument is doing behavioral cloning is like watching TV. Sometimes it seems to work very, very well in a weird way, because it's like watching yourself, which never happens to us, but that's what happens to robots. Somebody teleoperates these robots, and then the robots watch themselves. I say watch because they're not repeating it, right? The behavioral cloning happens in the head. They are literally trying to mimic what they did or what they were made to do, right? So it's a very bizarre world where it's like you're watching TV and you are there expertly doing a task, and you are now trying to frantically understand, what did I do in that particular moment so that this happens, so that I can keep doing this, right? But this is not how we learn. How we would learn is by practice. And part of it is because it's almost impossible for us to learn like that, because nobody can teleoperate us. But regardless, when it comes time to practice, the analogy is to try to think about, what is it that you're doing? You're doing a number of different things. You have some model of what you saw Cristiano Ronaldo do. In fact, you might even refer back to the video while you're on the field, right? And as you are doing the task, what you're probably doing is you are getting a rough sense of what Cristiano Ronaldo did with his legs, and you're going to try to do something similar. But then what you're actually going to use to evaluate how well you did is not the exact mean squared error between your legs trajectories and Cristiano Ronaldo's trajectories. Instead, you're going to see what happened to the ball when I hit it versus what happened to the ball when Cristiano Ronaldo hit it. So that difference is thinking about your impact on the world as opposed to your behavior is what is called emulation. And of course, we are not the first people to come up with emulation. People have thought about emulation for a long time. In fact, I think we cite like a paper from 15 years ago that gets at this point. It just mentions it in passing that you really need to be able to emulate if you want to imitate very well, which is the core idea. This paper just operationalizes it. So how it manifests in an algorithmic sense is that there is this imitation learning phase first in CIMER, and then there is this refinement phase or emulation phase where we focus on, I have this rough sense of how to move now, but I know that's not going to be enough. I need to now learn how to refine my movements, and I'm going to do this with reinforcement learning. And I don't want to design a bespoke reward for every task that I'm doing. My reward is going to be the emulation reward. And the emulation reward is simply about, in manipulation, what is the difference between what happened to the object when I did it versus what happened to the object when the expert did it. And this reward is the same across all the tasks. All you need to know is what is the object of interest. So now this lets the robot refine things. And we call them refinement because we don't just warm start the policy and just fine tune it. What we do is we say things like, this policy is already relatively good. It's just not very good. So if you focus on the manipulation problem, how this manifests is, if you're watching videos of like somebody cooking, let's say, right? That's a more close analogy to what we are doing in CIMER. You don't know anything about how much pressure they're applying to the objects that they are manipulating. So there is no force signal, there's no action data. So that's why this problem is about learning from just state-only observations. So the lack of that knowledge will need to be compensated for during when your refinement. But it's unlikely that you are going to substantially make changes to the way in which your entire hand or arm moves. What you're going to really change is fine-grained adjustments to your fingers. So this framework particularly just refines those degrees of freedom with the emulation reward. And we basically designed this and tried this across a number of tasks with the identical design, where once again, from an expert-free perspective, we force ourselves not to change any hyperparameters. You can't change anything. You just present this as a framework. Now you try it on a bunch of different tasks. And turns out that refinement process really has a dramatic impact on performance, as opposed to if you don't involve the robot in that refinement process. And of course, we also would compare against, like, what if all you did was just reinforcement, or what if you didn't have this emulation reward, or you had something task-specific rewards and stuff like that. It turns out you can do as well as a task-specific, well-designed reward, but you, in fact, do even better than those methods if you try to generalize now. This sort of refinement helps a lot when you're now trying to generalize across different objects, because it turns out you're learning more robust strategies. And we were even able to see the patterns that came up. For example, the robot kind of learns, like if it's trying to open a door, it needs to generate enough momentum to actually pull the door. And if it's trying to hit a hammer into the nail into a wall with a hammer, it's figuring out that hitting it at the center is probably much better. Different tasks had like these almost emergent patterns of how the refinements changed what the policy was. So that is basically the core idea behind CIMER.
Very nice. Key benefit from this, it's task agnostic, intervention free, achieves zero-shot generalization, and on a broader level, even if we look at the Codex framework where you use Koopman operators, it was far more computationally efficient, trained orders of magnitude faster than neural networks, LSTMs. And all of this ties to your lab's goals that we talked about at the start of the conversation, the efficiency, being expert-free, predictable. So now looking into the future, what do you think is the hardest to achieve in practice?
So for me, I think let me maybe answer this question from the perspective of like, what's going to be very challenging for techniques and the kinds of philosophy that we use in the lab. So one of the caveats that I anticipate will be a challenge is, how do you take these successes from still relatively narrow domains? When I say narrow domains, I mean, you might care about generalization across a wide spectrum of dimensions within your task or within the kind of manipulation that you're doing. How do you really find patterns that would work across the board? I'm not sure. So I'm saying it's challenging because it's not even clear if that something like that exists. I would go back to the argument of like, if you think of the robot's intelligence as either a monolithic single generalist model versus like this bag of tricks idea, there is also a similar question of, do you have a bag of tricks for structures? I'm not sure. Or is it that there are some foundational structures that would just work across the board? And even if they did, it's not like structures are incompatible with one another. Many structures are compatible in the sense that you could build off of things. So for example, in CIMER, we also use Koopman operator theory. We just didn't talk about it too much because it's not the focus of the paper. So you still have to do imitation, right? And while you're doing imitation, we just did Koopman operators because why wouldn't you? It's very, very computationally efficient and it's easy to use. So we might as well do this. So we can compose these structures together. So one of the challenges I anticipate is that we will find different breaking points for different structures. I'm still not sure how do we come up with a unified way of thinking about this. If I have a completely new situation that I can't, so it's almost like the unknown problem. I don't know. Right now, I have no way of knowing how to select the structures that I want to deploy? Or should I just fall back on learning completely a black box model? I'm not sure. I would like for the answer to be that I don't have to fall back on a full black box model, but nevertheless, I'm just not sure how to make this happen. Part of this could be a key challenge is maybe the robot can figure out its own structures. So this is very much analogous to thinking about the challenge of doing a representation learning on the fly. Except here, you are thinking about the general problem of how to constrain your own models, how to construct your own models. That's almost like feels like a very weird out there goal, but the idea is to see, can the robots figure out their own objectives? Can they figure out their own policy architectures? That's something I find fascinating, but I have no clue how to go about answering it yet. So I anticipate that to be a very interesting and important challenge.
You're always on uncharted territory, and as a result, there is a very high risk that you're going to be bad at some things. Yeah. And I also noticed your X cover page, it explicitly states that you should be brave enough to suck at something new. This is something that you're struggling with right now.
What am I struggling with right now? Finding a good balance in being an advisor. So this is something I'm slightly getting a better handle of after 4 years. But what I struggle with is simultaneously being very supportive of my students, giving them a lot of freedom, but at the same time, also figuring out how do you really create a culture where students feel capable, and you almost want to create a culture of excellence, but you shouldn't be doing it through fear. Right? You shouldn't be doing it with an iron fist. How do you strike that sweet balance? I know a few people I really admire who do this very, very well, but I don't think even those people can explicitly articulate how they do it. So I'm kind of trying to figure that out. I hope I'll figure that out soon. So that's one thing from like a meta perspective that I'm currently struggling with. From a technical perspective, oh boy, where do I start? There are so many problems and techniques and tools that I am struggling through by reading like tutorials and watching some of my colleagues give lectures, and I'm learning lots of new topics. Like, for example, the most recent one, or the most recent ones that I can imagine are I've been watching and reading a lot about self-supervised representation learning. So sometimes it's not enough to just know the basics. So you really want to become an expert in something to actually use those tools, even if you're not directly innovating in that space, but if you're still really going to use it for research. So most of the time in this example for that I mentioned, the self-supervised representation learning, almost inevitably it's very easy to feel dumb because you just don't know beyond a certain point. So I might know enough to teach a class where we introduce this topic, but I don't know enough about what is the state of the art. What are my colleagues in computer vision doing about this problem? So this requires reading broadly. This requires acquiring lots of new knowledge. So it's just that when I'm doing it, it's very obvious that I'm not good at this, but I'm working on a project that involves this. That means that I'm currently, as I'm learning it, I'm going to be kind of bad at it. I'm going to suck. If somebody evaluates me, somebody gives me a quiz, I'm probably going to fail, right? If I'm just studying. But the key is to not care about that. The key is just, that's what I mean by being brave enough to suck at something new, because you are always going to be in situations where you're learning something that you have not learned before. Same thing, I do the same thing on the dynamical systems and controls side. I'm a wannabe mathematician, but I'm not smart enough to be one. So I often try to learn new topics in applied math or mathematics that seems so bizarre and foreign and counterintuitive. So I feel very dumb when I'm doing that. But I still do it because I just like learning new things as much as possible. I've given up on stuff as well, right? Like sometimes I just don't have the time and dedication that it takes to truly understand certain topics, but I just give it a shot. And some things would just excite me enough that I will keep working on it, and slowly and surely I'll gain some amount of expertise in that space, enough to at least make meaningful contributions to my own field of expertise. So that's basically where that comes from, being able to completely be fine with not knowing stuff and learning new things.
Yeah, this is super helpful and reassuring for even graduate students that professors struggle with stuff too.
Yeah, no, I think it's, I mean, everybody struggles with things, right? Like it just is it depends on what you're struggling with. Like if you had asked me this question like a year ago, I would say, oh, I'm struggling. The biggest struggle would be learning to be a new parent. So there are always going to be personal struggles or professional struggles in one way, shape, or form. It's just, it almost is like, it'll be kind of boring if you had no struggles, wouldn't it? Right? Like it'll be kind of boring. So you always want to operate at the edge of your capabilities so that you have the right amount of stress and motivation. So you don't want to be such that like almost everything you're doing is very challenging. Then I think it just is a recipe for just feeling miserable. Nor do you want to just work on stuff that's just almost too easy for you all the time. You will get bored. And this job is like a magic job where you can just do whatever you want. And if I can't do it in this job, I don't know how I will ever do it.
Yeah, one thing that I love that you said was I always disassociate my self-worth from feeling dumb. If I feel dumb, that's not a reflection on my self-worth. What place my sense of self-worth on is the process, the scientific process and showing up daily. And it's really important for everyone to hear that. And I also wanted to ask you, in terms of mental wellness, as you've been a graduate student, you've been a professor, what are some activities that you've taken on that have helped you balance your mental health?
Sure. Once again, I would say I have not been disciplined enough to just do this all the time. I'm not a beacon of shining mental health, certainly not. Uh, I Things that have helped. I'm married to a psychologist. That helps. But if you're not able to be married to a psychologist, there are, of course, other things you could do. For example, I love nature and hiking. I get a lot out of it. So I'm not able to do it as much since having a kid, but I used to hike a lot. That would help me a lot. And in grad school in particular, I had a good group of friends. And I think I would have been miserable without them. I always had, we had a relatively large group of friends. There was always something fun to do. So I had a very full life outside of the lab, which was very helpful instead of just feeling like I'm just a PhD student trying to crank out stuff. So in fact, if you have good friends, like they would force you to participate in activities, even if you're busy. So you can sort of, you will learn to prioritize well, and you will learn to do other things outside. And even when things are relatively tough, which happens for everyone, almost like in a seasonal way, having a lot of friends certainly helps. So that's one. And during the pandemic, I picked up meditation. Meditation helps a lot, just to kind of slow down and for just at least like 5-10 minutes a day, just not do anything, just drop all pursuit and just sit and be like, okay, I don't have to do anything right now. I find that very relaxing. I find that very refreshing. It's almost a perspective. Otherwise, at least for me, I don't realize I'm frantically just trying to achieve something constantly. I don't have to. I could just chill for a little bit. So I like that a lot.
Yeah, it's very rare to see you sit still because whenever you're giving lectures, also you're just like pacing from one end to the other.
It's probably the ADHD, but even now, like I'm kind of fidgeting with something that is always there. But that's another thing that meditation is interesting too. So you could just sit and watch sort of your desire to fidget and your desire to just move around. I do move around a lot. And that meditation certainly helps generally across the way. It's just this, for me, it's just a matter of perspective. So it's a very unique perspective to every other perspective that I get because it almost makes certain things that we stress over comical and kind of shows like how almost we are all just hilarious in the sense that we are pursuing stuff that if you really think about it, doesn't really have meaning. We just attach meaning to stuff and we just want to feel good about ourselves, whatever it is. But this perspective is very hard to live with, right? Like I'm not a monk. I wish I had that kind of wisdom. I certainly don't. So I enjoy having that wisdom for like 5 minutes.
Yeah, so there's certain things you can accept intellectually, but you can only really understand it when you live it experientially. I wanted to end this conversation with, on a more selfish note, what advice would you give to people just entering robotics and AI research and to make the most of this journey?
Okay, so I'm going to give you an advice that's selfish in return, in the sense that, so everybody believes whatever their core philosophies are, right? Including scientists. Like I mentioned, we all have our like pet ideas, pet views of the world and so on. So For me, what I really want the next generation of scientists to be thinking about is I want them to have a very open mind. What I mean by that is when you start out, it's relatively easy to kind of buy into a narrative. And it's inevitable. In fact, that's what inspires most young people to get into a field. It's this fascination, it's this sort of like magic almost that you feel attracted to. You're like, AI and robotics sound really cool. This is awesome, which is great. But my advice to them is it's almost a caution to not fall for a particular point of view or a particular worldview. Instead, wait until they form their own opinions. They're eventually going to form. You're going to eventually form your opinions. You're going to take a stance, like it's inevitable. But don't prematurely do it before you have sufficient experience. You can work on anything you want, right? That's fine. Like it's a function of, obviously, you can't just work on whatever you want independently. You would need an advisor who would fund you, who would be able to help you through stuff. So you're somewhat constrained. But a PhD is just a license to do research. You're not beholden to work on the problems you work on during your PhD. You can do whatever you want once you graduate. A PhD is literally just a license to be a scientist. Like all it says is like, oh, this person, we think this person is capable of being a scientist, right? That's what a degree is in PhD. So treat it like that and really think about the kinds of things that you want to work on. Question your own work, right? Be very humble. And ultimately, the same thing that you refer to, which I mentioned to you earlier in an earlier conversation, don't attach your ego to your ideas and your papers or whatever it is. So that way, you don't feel this intense pressure to defend your ideas and almost fool yourself into thinking your ideas are correct. You should always be open to the fact that what you've been thinking for a long time is completely false. And you now have to change your mind. And you really have to be ready to change your mind. And the way to actually do this, at least that I know of, in a reliable way to do this, is literally expose yourself to differing perspectives and carefully listening to people who disagree with each other. I think this might sound like, oh, relatively simple, but for you to actually have an emotional response to things that was compatible with this philosophy, you genuinely need to just be open and listen. So if you're working in classical approaches, for example, attend talks and seminars that are about scaling robot learning. And genuinely ask yourself, am I disagreeing with these ideas because I don't like the way they make me feel about my own? Or is there an actual disagreement that I have? Chances are you probably have a nuanced disagreement, but many things that they are saying are probably very true. Similarly, if you're a person who's working on data-driven techniques, you're just building foundation models, or your lab builds them and you're building them right now, force yourself to go to seminars where control theorists talk about robots. They're going to get some things wrong. They're going to get some things right. Go listen to people who are going to talk about methods that have nothing to do with data or learning. If you listen to enough perspectives, you will start to see that it's not binary. Everybody has a perspective, and that perspective has some value. And you can then decide, do I want to go towards one perspective, or do I want to reject all these perspectives and create my own? So in many ways, one way to think about my own philosophy of research is that I'm indecisive. It's because I find neither argument of I don't need scaling or data to do this, or I only need these things. I find neither of those arguments convincing. So I'm happy to be in the middle. So of course I can intellectualize this and make it seem very smart, but you could also question whether I'm just being indecisive. But I think it's good to be indecisive sometimes. So have a skeptical view is what I would ultimately give as advice. Like I mentioned, it's a very selfish advice for influencing the next generation of scientists.
Yeah. Professor, I have to say, this is truly fascinating speaking with you and you covering so much. And I wanted to also tell you that it's really nice to see someone treat you like a peer and actually speaking to you in a way that you would understand. And I know that the audience would appreciate it as well.
That's very kind of you to say. I appreciate this opportunity. This is really fun. I'm glad you're doing this. This sounds really awesome. I'm very glad that you're doing something like this. I'm sure you're having fun and learning a lot, but at the same time, I also really appreciate just doing something like this, which will benefit people who are listening, which will just benefit generally the kind of things that how to translate some of the things that are happening in research labs and make it more accessible to the general public. For example, there is a reason why we didn't sit and talk about mathematical equations and the nuances of these methods, because that's not the point. There are other avenues where people can learn about those things. But these kinds of avenues are not as common. So I'm very glad that you're doing something like this. That's awesome.